Gauss's theorem is going to be our last theorem that that has that fundamental theorem of calculus feel, and we want to try to look at the similarities between the big theorems that we've had from Green's to Stokes to Gauss. Now, Green's and Stokes are essentially the same theorem, except Green's is in 2 dimensions and Stokes is in 3. But the divergence theorem is something a little bit different. It's actually bigger. It's happening in 3 dimensions. And another theorem where we go from some multiple integral down to one less integral. I know from left to right it looks like we're going from a double to a triple integral, but if we want to think about the fundamental theorem of calculus, how we're taking the integral of a derivative of something, turns out that the div is like a derivative of something. So let's talk about this. E is a simple solid region. So it's a 3-dimensional region. That's your base, that's your geometry that you're integrating over for a triple integral. You have a solid region, and S is a boundary of the surface, or it's a boundary surface of E. Now, what kinds of things can you tell me about S? Not necessarily. It encloses E, right? So imagine a box or a sphere. If we just look at a solid sphere in 3 dimensions, then S would be the outside of the sphere. If you imagine 1/8 of the sphere that's like in the first octant, where X is positive, Y is positive, Z is positive, what would S be? So if we're just looking at the front part over here of the sphere, what would S be? Yeah? No? It would be the surface area of the sphere? The 1/8 of the sphere? Not quite. The boundaries of the walls, the floor and the sides, would also have to be part of that S. Does that make sense? So, for example, if I were to, on a graphing calculator, just draw that surface, and I'm going to draw it using spherical parameterization. How does it go? Cosine sine, cosine U, sine V, sine U, sine V, and cosine U or V. V, and then we'll have it go from U go from 0 to pi over 2, and V go from 0 to pi over 2. Did I do pi over 2? So this is not, if we're talking about the 1/8 of a sphere in the first octant, this is not S. This was not totally enclosed S. So what we would need is be those other sides, the bottom, the side walls. Okay? We need a plane, but we can't just throw a plane in there, right? Because I mean, you can. That's too big, right? We only want the small bit of the plane that's going to be covering the sphere. And so for that, I would need to parameterize again. Yeah. By the way, how would you get this? I mean, how would I parameterize this using U's and V's? Yeah. Well, I was going to do some extra credit stuff for you guys to try to come up with parameterizations for pieces of things. That's about as vague as it gets. Huh? Yeah, well, for this one, but when I work on a new equation, it doesn't matter. And so sometimes I like to scale this so that I'm going from 0 to 1. And so usually if you multiply the parameter by however far you want it to go, it'll get scaled from 0 to 1. So, did it draw it? Oh, these are all U's. I need to change this into V's. So sometimes it's useful to scale things if you're trying to graph pieces of it. And so here's another one. U cosine V cosine pi over 2V U sine pi over 2V, and this is just flat on the xy plane, so we'll call it 0. So if I trim the plane to make it just the bottom part, here's the floor that I would need for that surface to encompass that whole thing. And then you would need 2 more sides to work it out. So it'll just be these. Why don't I just finish it, since I think it'll be quick. I think if I just switch one of these, that would get me all my sides. Do I have everything? Yep. So I have all the sides together. Now I have fully enclosed this solid with 4 surfaces. Okay? All right, so I was trying to get something out of you guys. What is S? What can you say about S? It's a closed surface. So S, because it has to totally encompass a solid, S has to be a closed surface. And so with a closed surface, it would make sense for us to talk about an outward or inward orientation. And here the orientation they're looking for is an outward orientation. To call it a positive orientation. Yeah?
So, just correct me if I'm wrong, but didn't we say that in order for it to be a closed surface, like at least in this particular case, that all 3 of the principles have to have some sort of
Yeah. Well, they would be needing, those boundaries would be sealed. Yeah. All right, so F is a vector field whose component functions are continuous and the partial have continuous partial derivatives in everything that's in the region that we're talking about. Then you have this statement. So notice that this is a triple integral dv. So this is our regular triple integral, and this is a scalar. And then what you have here is a triple integral. And then on the left-hand side, you have a flux. Well, first let's talk about S. S is going to be the boundary of E. And so sometimes you might see me write it with the partial notation again, E. So that's our notation for the boundary. And then this is a flux integral. In your experience, what seems to be easier to compute, a flux integral or a triple integral? Flux is easier?
Well, it depends.
It kind of depends on stuff, but I think in general, triple integral is a little bit easier to compute because you're dealing with scalar functions. Now, you have 3 dimensions, sure, but we kind of got used to double and triple integrals already, and so when we come to the flux integrals, we have to actually parameterize the surface, and so it turns out that parameterizing the surface may or may not be so easy. So I think the triple integral generally is an easier integral. But when we're talking about this in terms of trying to relate it to all the stuff that we've been working on, you can say the integral of a derivative over a solid is equal to one less integral of the original function over the boundary. Now, if you look at the little scribble that I did over Stokes' theorem, or under Stokes' theorem, you'll see that the words almost matched up. We're talking about integral of a derivative of something. We're talking about one less integral of the original. And we're talking about a geometric object. And on the other side, the boundary of that geometric object. So if you bring that all the way back to the fundamental theorem of calculus that you learned in Calc 1 and Calc 2, it's essentially saying the same thing. And that's what's really interesting about this, is that it's all big generalizations of the fundamental theorem of calculus. Okay, let's take a look at some examples and see what we could do. I don't know if I logged in yet. Nope, I didn't. So a good task is to imagine how you would solve for something by doing both sides of the equation. In most problems, in reality, you'll probably be using one side or the other, and most likely in this case, you'd be using the triple integral, because a lot of times it'll end up being a little bit easier. Well, let's take a look at this problem here, the first one in the section. So verify that the divergence is true. Divergence theorem is true for the vector field 5x, xy, 4xz, and then the cube bounded by the planes x is equal to 0, x is equal to 2, all that stuff. So let's first do the flux integral side of things. And so what we have here is we have the surfaces that would enclose your solid. There should be 6 surfaces. I'm not liking this already, but let's do it anyways. So first, let's compute the flux over the surface. And since there are 6 surfaces, we're going to have to do 6 surface flux integrals. Let's just get this all straightened out. We have x is equal to 0, x is equal to 2, y is equal to 0, y is equal to 2, z is equal to 0, z is equal to 2. So at least they're all the same. So when we look at integrating over this and parameterizing it and stuff like that, we'll see that it's going to be all over 2. So let me rewrite our vector field without the i's, j's, and k's. If you guys are used to using the I, j's, and k's, you can feel free to go ahead and do that, and they do that in physics. But I changed my notation a little bit. All right, so let's do the surfaces one by one. Remember, there's going to be 6 of them. So let's say S1. Let's start with z is equal to 0. Let's see if we can keep track of this. So the parameterization for this is going to be, you have z as a variable. It'll be a function of x and y. Oops, sorry, not equal sign. Let me get this written up properly for the first couple at least, and then we'll try to simplify things. So the parameterization will be x comma y comma 0. Your RU cross RV should just be, well, the normal vector is just going to be, which way is the normal vector going to go? I think I would be, these are planes, so I would be really, really interested in considering the other form of the flux integral, which is integral S F dotted with N. Which way is the normal vector? Yep, so it would be going down, right? Because it's an outward normal. -1. There was a negative sign there. Just couldn't see it. I can't see it. Yeah, I need those bifocals now. I've been trying to tell my doctor, no, I don't need them. I don't need them. I do. So if I dot this, let's see, F dotted with N. It's nice that there's a bunch of zeros here. So this will just be 4xz, right? But z is equal to 0 when I put this, when I put my parameterization in here. So that whole thing is going to be equal to 0. All right, I would put x is equal to x, y is equal to y, and z is equal to 0, and it's equal to 0, so I get nothing. That was nice. Yeah?
How did you get how do you know the parameterization of that variable? Is it because z is constant?
Yeah, you can think about z as being a constant, or you can think about just parameterizing this as x, y, 0. I mean, we can use u and v, right?
Yeah.
So, so this is the kind of like the parameterization practice that I wanted you guys to do in one of your, quizzes. So z is equal to 0, or u comma v comma 0, and then z goes from 0 to 2, or x goes from 0 to 2, and y goes from 0 to 2. So this is pretty much what we're looking for in the parameterization, right? And then if we do the other one, where we have z is equal to 2, which is what we're going to do next, then you have those parts of the square of the cube. Okay? And I could have used u's and v's, but x and y just seems more convenient. I can't do x and y here because it'll give me some issues, but that's the program's fault. So we have 0. Let's put a box around that. All right, let's maybe do some alternating colors here. Let's say S2 is when z is equal to 2. So your R of x, y is going to be equal to x comma y comma 2, which is that parameterization I just had. And so what's your normal vector going to be in this case? Z will be positive, right? So you're up here now, you're on this plane, and since it's a flat plane, horizontal, it'll just go straight up. So that's just 0, 0, 1, or k. And so if you dot those two things, f dotted with n, again, I'm looking at f up here, dotted with n, the 0, 0, 1, you just have 4xy, or xz. So x is x, y is y, and z is 2. So given the substitution here that you need to make, you get 8x. X is x, y is y, z is equal to 2. So you have 4x times 2, and you get 8x. So it's not 0. We actually have to follow through with some integration here. So we got the integral. This will end up being a flux integral over S2 of 8x, and actually what? Yes. Surface integral. We didn't talk about the domain, but regardless of which function we're dealing with or which surface we're dealing with, the domain is going to be constants from 0 to 2. So depending if this is an xy or a yz or an xz surface, it's always going to be 0 to 2. So that's the nice thing about the cube. So our integral is going to be we need the it's going to be 1. Yes. I just have to do the calculation in my head. So remember that your ds, without the arrow on top, your ds is like the square root of fx squared plus fy squared plus 1. But your f function in this case is constant. So the derivative of that is 0. So your differential surface area differential is just going to be 1. And it's going to be 1 for all these things. So let me squeeze in a 1 here. And then let's set up the integral now. We got integral from 0 to 2, integral from 0 to 2, 8x dx dy. So, I don't know. Let's see. Let's break this up to different pieces. 0 to 2 dy, integral from 0 to 2x dx. So 8's constant, and then dy is just going to be dy. And then we have x dx, which is x squared over 2. So I don't know. What do you get? You get 8 times, this is going to be y from 0 to 2. And then this is going to be x squared over 2 from 0 to 2. It'll just be 2 again, right? Sorry, I'm forcing you guys to do these integrals in your head. Write it out, and it's quick enough to write out. I just don't want to. What is this? 8, 16, 32. Yeah. Okay. 2 down, 4 to go. All right, let's do the y. S3. Let's just say this is the y is equal to 0 plane. So the parameterization. Now, I'm looking at y is equal to 0, so the shadow that's going to be on the coordinate plane would be on the x, z plane, right? So let's parameterize this with x and z. So x is x, y is 0, z is z. You want to use u's and v's? We're kind of doing it this way already. Yeah. Okay, so your normal vector here would be what? This is y is equal to 0. That would be this plane over here. Minus 1, 0, 0. Close. The minus 1 would go on the y component. Yeah. All right, so let's dot this. F dotted with n. This is our f. You got negative 1 and 0 for the other two that would cancel it out. And the y is equal to 0. So that would make the whole thing 0. Kind of seeing a pattern here, right? The 0 coordinate planes will probably going to be 0. Oh, there was another missing integral here. So the flux for S3 is going to be 0. Yeah.
So this is what we're doing. So the vector field's up there. So how did you just dot it? Oh.
Dot it with the vector field up here. So this is always looking at the vector field. So I'm taking my normal vector in the vector field. All right. Let's try the right side now. So your R in this case would be still a function of x and z. X is x, z is z, and then your y now, you're looking at the y is equal to 2 plane. So this is a 2. Normal vector is going to be in the positive direction now. So f dotted with n is going to give us a positive xy. And x is equal to 2, or y is equal to 2. X is equal to x, y is equal to 2, so this is 2x again. Right? So let's throw that into the flux. Well, actually, let's go straight into your double integral. So it'll be 2x, and then again, there's that 1 that would have come up with this change from a surface integral to a double integral. And then we're using the same domain from 0 to 2 in both variables. And then we would integrate that again. So let's take the 2 out, integrate from 0 to 2 with respect to z, integrate from 0 to 2 of x dx. So we got 2, a 2, and this integral again is 2, x squared over 2. 2, 4, 8 this time. All right. We're finding a pattern here, so there's a good chance that this is going to be 0 again. This time x is equal to 0, so the y and z would be your variables left over. 0 in the x, y, and z in the other two components. Our normal vector would be going straight at you if you look at that box. No, I'm sorry. If x is equal to 0 is the back of the box, and it's pointing backward. So that would be a negative 1, 0, 0 for your normal vector. And then if you take f dotted with n, you get negative 5x. But when you plug in the parameterization, since x is equal to 0, you get 0. So once you get this f dot n, you used to have x, y's, and z's in there. You plug in all the values that you get so that you can reduce it to the two variables in your parameterization, and then you get 0. All right, last one. This is x is equal to 2. So our parameterization in y and z again is equal to, this time our x is equal to 2, y is equal to y, z is equal to z. And your normal vector, the front of that cube will be going towards u, which is going in the positive x direction. And then if you dot this normal vector with the original function, you're going to get a positive xy, or positive 5x, which is going to be 5 times 2, because x is equal to 2. So over our domain, we have a constant 10 that we're integrating, and that's just a constant 10. So we have a 2 by 2 square, right? So 2 times 2 is 4. So 10 times the area of D, which is 2 squared, and we get 40. 48, 32, 80. So adding up all those flux integrals would give us the total flux, which is going to be 80. Okay? Yeah, it is a lot of surfaces. With 12 sides. So this time, let's use Gauss's theorem to see if we can simplify our work a little bit. We have the inside, solid inside of that box as our E, which we can easily represent as, if we need to, constant limits for our triple integral. So remember, whenever you have constant limits for a double or triple integral, you're looking at rectangles or boxes. If your shape is somehow curved, it's somehow part of a sphere or something like that, then you're not going to have constant limits. So anyways, the first thing, it looks like the first thing we need to do is take the div of f. So this is our f. The div is the derivative of the first component with respect to the first variable x, plus, it's like the dot product, right? The derivative of the second component with respect to the second variable y, and the derivative of the last component with respect to the last variable z. So that's your div. Well, I think that simplifies to 5 plus 5x. And so that's what's going to go inside of our integral. So we have a triple integral. I'm going to set this up already as a triple integral of 5. I'll just keep the 5 plus 5x. Okay? It looks like the only variable I have here is x, so the other variables I can take out and do it separately. So I can integrate from 0 to 2 with respect to y, integrate from 0 to 2 with respect to z, and then do that separately from the integral from 0 to 2 of 5 plus 5x dx. I mean, I should have taken out the 5 too, but I'll just leave it there. So the integral here is 2. The integral for the second one is 2. This one will be 5x plus 5 over 2x squared from 0 to 2. So this would be 10 plus 10. This is 20, right? Yeah. So it'll be 4 times 20, which is 80. So the same answer that we got using those 5 or 4 or 6, 6 surfaces. And here we just combine it all together. And so which one was easier? Yeah, I'd say so. We should check our answer. I hope it's right. I mean, we got 2 different ways. You got the same answer. You should be right, right? Right. All right. This one? Verify, so I guess it's asking you to. What?
But I'm saying for the ones on the homework, you're going to
Do you have one of these things in your homework where you have to fill in some information? Hi.
get one of those. I'll link it.
Mm-hmm. All right, let's do number 5. This is a collection of all the problems that that's available. It's not necessarily your homework. So use the divergence theorem to calculate the surface integral or the flux integral of f across S, where S is the surface of the solid bounded by the cylinder. Y squared plus z squared equals 1. And the planes x is equal to 1, x is equal to 3. So I think I'll have a plane here where it intersects a circle. I mean, it intersects a cylinder in a circle. And then I have another plane back here behind the axis. This goes behind. I don't know if you can tell it goes behind. I don't know if I drew it like it goes behind. But so x equals 3, negative 1. Now, if you were to do the flux directly, what would you need to do? Let's think about it, talk about it, and not do it. But you should know what you need to do to be able to do this. You would need 3, right? You would need 3 surface integrals. So you would need the surface integral for the first surface, maybe the front face, and then the back face over here, and then the cylinder itself. And so you would need to compute 3 surface integrals. And then add them all together, so you need to parameterize them. So parameterizing the 2 sides probably is not so hard, but you'd have to parameterize the cylinder, which could get a little tricky, and you should know how to do that. And maybe I'll see if we have time to talk a little bit about that. So instead of doing this, though, we're going to opt for the divergence theorem, also known as Gauss's theorem. So I'm not going to write it out. Let's just get to the calculations that we need. We need the div of the vector field. Again, it's taking your value here, and then you're taking the derivative of each component with respect to that component position. So the first component with respect to x, so the 3 and the y squared are constants, and x is just an x. So I'll have a 3y squared there, plus with respect to y, x and z are both constants, so this is going to be 0. You don't need to put that there, but I'll put it there so that we can see what's happening. And then this last one with respect to z is 3z squared. Okay? So if we call this solid cylinder our region E, that doesn't even look like a cylinder. Oh, that looks a little. Let's make sure he drops nice. You guys see that little video clip of some news anchor or somebody that was drawing something and it started to look a little obscene? She tried to cover it up. Well, anyways, this is a cylinder E. This is your solid, and so you're going to do a triple integral of a solid of 3y squared plus 3z squared dv. So we need to try to see if we can find limits for this. Now, since this is a cylinder that's moving along the x, it makes a nice shadow on the YZ plane. And this is a cylinder radius 1. So instead of finding limits for the y and the z, which is what I would normally do, I'm going to leave it like that because it's circular, and instead of dealing with y and z, I might just go to polar coordinates with that. But the x still has some bounded limits, but fortunately it has constant bounded limits. So where is x going to go from? Yeah. X is going to go from -1 to 3. That's just how the x is going to go, and it's constant. And then instead, like I said, I could try to make a circle out of this and have the equation of the circle and then solve for one of the variables. and then put that in for the y and the z. Instead of doing all that stuff, I'm just going to consider this as a two-dimensional region for my two variables and change that into polar. Now, we're used to seeing x and y in polar coordinates, but there should be nothing to stop us from looking at y and z in polar coordinates. I mean, I'll write it out, but I don't think we need to go through all this. But we can say that y, suppose y is equal to r cosine theta, and z is equal to r sine theta. Then we got y squared plus z squared is equal to r squared. Now, it seems handy, right? Because of our integrand. And then not only that, but we can have our y limits and z limits changed into r and theta limits. And this has radius of 1, and the theta goes all the way around to 2 pi. Oh, I should have started to work on the integral first, but oh well. We're here now, so let's see. Our we'll integrate with respect to x from -1 to 3. And then let's make the conversion into polar coordinates. So we have our dx from 1 to 3. We have our integrand as 3r squared. And then when we change into polar coordinates, we come up with an extra r, and then a dr and d theta. I don't know if I should have done it that way, but probably would have taken some intermediate steps. Three minus -1, yeah. Yeah, is this okay? This step over here? So I feel like I should have integrated one time first, and then change into polar. We're technically kind of doing cylindrical coordinates because we're kind of doing this in 3 dimensions. Except instead of x, y is r and theta, the y, z is r and theta, and then the x is equal to x. All right, yeah, so we can split this up. There's no x's, so we could take the x integral separately. There's no theta, so we can take the theta integral separately. And then the 3 is a constant. We can take the 3 out. And then the r is 0 to 1, r cubed dr. Okay? So we got 3, we got the length here, 3 minus -1, we got 2 pi, and we got r to the 4th over 4, so cancel out with this 4, and then that's it. All right. Six pi. Which one was it? Okay. All right. Let me talk about another problem that could come up. So remember, for the Stokes theorem at the end of last class, I talked about a scenario where you have some weird surface, and then it's the same thing as if you flatten it out. So there's another scenario that we could take a look at for the divergence theorem, for Gauss's theorem. And then suppose you had an open surface. So let's say you had a sphere, a half of a sphere. That was open. And you're trying to find the flux of some F going through this. What you can do is that if you feel like the divergence theorem would be helpful, you can cap this off with a cover. Right? So even if it's an open surface, you can close this with a cover, and then you can use the divergence theorem. So let's see. What do I mean by that? And how would that actually work? So suppose you have S, and you want to find the flux. Okay? Well, if you cap it off with this S1, so if you cap it off with S1, now you have a closed surface. So this put together would be a flux of a closed surface, which now you can use the Gauss's theorem, right? So if this turns out to be a little easier to work with, then it might be worth computing a triple integral. You're taking the div of some function, so that might simplify things a little bit. And then you would cap it off with a nice flat surface that might make this a little bit easier to compute as well. And so by subtracting this over to the other side, you might come up with a nicer integral. All right, so we'll do something like this next time, where we have some complicated solid. The quiz that you guys will do over the weekend, I just have to double check one thing, but I have it available. It's not up online yet, but I just wanted to have you guys take a peek. So I have two quizzes. One of them goes over the fundamental theorem of line integrals. And what I'm asking you to do is to compute the line integral directly. And then according to the fundamental theorem of line integrals, all you really have to do is find the potential function and plug in the endpoints. Right? So that's what this is going to do. Number one in this quiz will be kind of a long process. It's not that long. You have two curves that you're integrating over, and so you're going to have to do 2 line integrals. And whatever you get from that, you should have the same answer as using the fundamental theorem of line integrals. But again, I'm not interested in the answer. I'm more interested in the process of you computing the line integral. All right, so that's the first quiz. The second quiz is using Stokes' theorem and using both sides of Stokes' theorem. So Stokes' theorem has a flux of a curl that you have to compute, and then it has a line integral over a closed curve that you have to compute. So I want to see the work for both of those, and then you should eventually get the same answer. So this is the one that I'm still working on. I want to make sure that this is actually doable. And what happens when you start making up problems and at this level of math, sometimes it doesn't work out and then it gets impossible to compute. So when you get to the integral part, the working integral, you can, if it's easy enough to do, you can just do it by hand. But if it gets too complicated, I'd say if you had like a sine squared in it or something, I know you can do that. But you're also welcome to plug it into Wolfram Alpha to see what you get. Okay? But I want to see most of the work, setting up, drawing the figures that's needed, and all that. This will be due on Monday. Yeah. So I will have that posted. I'm looking for a review to post up, and I can't seem to find any old reviews, and that made me think that I didn't give a review for the final exam. So I think what I've done in the past is I've just picked out some problems from the book for you to look at and see that could be some things you can study. So I'll try to do that this weekend as well. Okay, but I'll post a quiz up by the end of today. All right, see you guys on Monday.